This programme covers carbon manganese steel and how to weld it using the gas metal arc welding process, also known as MIG welding. To start with, we'll explain the different types of carbon manganese steels, their properties and applications, and then move on to the practical aspects of welding these materials. So it would be helpful if you had a basic knowledge of the principles of gas metal arc welding.
Iron has been used extensively since it was first discovered around 1000 years BC. It's likely that it was found by chance after an oven being used to make charcoal was built over rocks rich in iron oxide. The intense heat at the base of the oven and the oxygen-free environment would provide the necessary conditions to reduce the ore, producing a nodule of iron metal. The iron-making process has been fine-tuned and scaled up over the centuries, but in essence it's still the same today as it was in those first early ovens. Iron produced in blast furnaces is full of impurities and has relatively poor mechanical properties. But in the steel-making process, the crude iron is refined by passing oxygen through it to burn off the impurities. What is left is a material which has excellent strength that can be formed into any shape and used in almost every engineering application. As technology has developed, engineers have demanded steels with higher and higher tensile strength, together with adequate toughness. By increasing the carbon content of steel and providing the appropriate heat treatment, it was possible to greatly improve the material properties. However, the limit by using this technique was very quickly reached, and other means of improving the steel's properties were required. This is achieved by alloying with other elements, allowing steel to be used for applications from motorcar bodies and supporting girders to ball bearings and steel wire. Mild steel is the generic term for the majority of carbon and carbon manganese steels. These steels typically contain between 0.05 and 2% carbon, 0.3 and 2% manganese, up to 0.6% silicon, and many other elements such as nickel, chromium, tungsten and aluminium, which are put in deliberately to alter the properties of the steel, allowing it to be used for a wide range of applications. Some alloying elements are only required in small amounts in order to improve properties such as for high-strength, low-alloy steels. These steels contain small quantities of aluminium, vanadium, titanium or niobium to enhance their mechanical properties, providing high-tensile, tough materials for structural applications, such as offshore rigs and pipelines. Additions of nickel to carbon manganese steel improves toughness at low temperatures for cryogenic uses, and by adding molybdenum and chromium, the creep resistance of the steels improve, allowing use at elevated temperatures. All these steels are resistant to hydrogen cracking and to the detrimental effects of sulfur-bearing hydrocarbons, making them particularly suitable for the petrochemical industry. The majority of all welding is carried out on carbon and carbon manganese steels, and to ensure successful welding, it's usual that the steel has a carbon content less than 0.35% in order to reduce the risk of cracking. The weld thermal cycle will, after the carbon and alloy content of the steel, be the most significant factor in influencing the strength of the weld area. The three important phases of the cycle are first, the maximum temperature reached, secondly, the time held at that temperature, and finally, the rate of cooling. For thick sections over 25 millimeters, it might be necessary to preheat the joint area to around 100 degrees centigrade, and it's often necessary to heat treat the whole joint afterwards in order to obtain the optimum mechanical properties. Mild steels can all be welded by any of the commonly used welding processes, but gas metal arc welding allows good welds to be made whether the operator is welding thick sections in industry or an enthusiast repairing a car. Using the correct shielding gas in gas metal arc welding is essential in order to achieve the best quality weld. Shielding gas mixtures which contain argon, carbon dioxide and oxygen are designed for successful welding at all current levels and transfer modes, and are the ideal choice. But welding can be carried out using argon carbon dioxide mixes and even pure carbon dioxide.
Well, with the help of Mel, we're now looking at the equipment used and the consumables. What are we using today, Mel?
Yeah, the choice of consumables and equipment is dependent on certain factors: the composition of the carbon manganese steel that we're welding, the position that's going to be welded in, and the thickness of the material. For thin section work such as this, we'd use a small diameter solid wire and probably a light industrial unit such as this one. For heavier section work, the diameter of the wire would be larger, or maybe even a flux cord wire, and a larger output machine such as the one behind you.
Right. What about gases?
Traditionally, the gas that was used was carbon dioxide. There are some drawbacks to its use. It has to be heated before going into the regulator to prevent freezing. It produces quite a lot of spatter when used in the weld, and also for thick section weld, it won't achieve spray transfer.
Right, so things moved on.
Things have moved on. Some people are using two-component mixtures, which are argon plus carbon dioxide, but for solid wire work, we would recommend a three-component mixture, which is argon plus carbon dioxide plus oxygen. Again, the level of carbon dioxide in the three-component mixture is dependent on the thickness of material. For the thinner section work, the carbon dioxide level is lower. For thicker section work, to aid diffusion, we use a higher CO2 content.
Right. Could you just explain some of the joints that we'll be welding today?
Yeah, we have the four major joint types, which are when the plates overlap each other, it's a lap joint.
Yeah.
When they meet at a corner, it's a corner joint. When they meet at right angles like this, that's a fillet joint. And we have a butt joint when they butt together in the same plane. Now, for thin section work such as this, it's quite acceptable to have a square edge and no gap. We will achieve penetration. But as you increase the material thickness, so you'll find that you have to initially start leaving gaps to attain that penetration, and then for this sort of section work, we're using a single V. We put a bevel on each plate. We're also putting a root face on the plate to aid the penetration, and we would leave a gap. For even thicker section work, such as the one near you, and if you're able to get to the reverse side, we use a double V.
Right, that's a really thick section. And so what you're aiming for is filling that gap with weld, aren't you?
Completely filled up, so it's completely fused throughout the thickness.
Okay, I can barely move that, but let's try and weld it now and set the equipment up.
Okay.
Okay, Mel, so what do we do first?
Well, we've connected the shielding gas to the machine. It has the regulator. We've also got a flow indicator on here that gives an accurate reading of the flow that's going to be used. In this case, we're going to use about 18 litres per minute. But that's connected to the machine. The wire is on. We're using 1mm A18 type wire. That's fed through the wire feed unit, and you can see that we have wire feed rolls in here that have different grooves for the different diameters of wire. There's a tensioning device here that can be adjusted for the different diameters of wire. The wire is then fed through into the torch, and there is a liner inside this torch, and for carbon manganese steel, it's that type of liner that is recommended.
Yeah, quite robust.
It's fed through to the end of the torch, and here you have the gas diffuser, and you can see the ports there that allow the gas to pass out. The contact tip is now fitted to that. There are different diameters of contact tip for the different diameters of wire, but this is where the welding current is actually picked up. It also allows you to quite accurately guide the wire into the weld pool. Now, you can see there that we have two different types of gas shroud, one being shorter than the other. The short one is for dip transfer. This is for low amperage work where you really need quite close stick-outs and quite close control. The longer shroud is for spray transfer, where you're going to have a much larger weld pool and you must have good gas coverage, and this aids the gas coverage. We're going to start with dip welding, so we'll fit the nozzle to the torch. Now, the machine itself, the wire feed unit here, the major controls are the wire feed speed and amperage. We also have a wire feed button where the wire can be fed through the machine without the welding power being involved, and a gas purge button. It's important to always purge the line, particularly in the morning before you start, to rid any moisture. On the front of the panel itself, the voltage controls. We also have an ammeter and a voltmeter on this particular machine that gives us our welding parameters. You have a low range and a high range voltage control, and on this particular machine, a sliding voltage control, so we can quite accurately set welding conditions. The power cables themselves, we have the earth return lead going back into the machine, and here this lead is taking the welding power up to the wire feed unit. You can see there are two inlets for this. This is the inductance, and this is of importance in dip transfer in that it determines the amount of time that resistance heating is allowed to build up in a wire before it necks off. For this particular application, I think we'll probably be best on that inductance tapping.
Right. Okay, so we power up. Right, we've obviously got the protective clothing on, Mel.
Yeah, welding's emitting heat and radiation. We've got to protect the skin from burning. We're also wearing head shields and quite thick leather gauntlets.
Yeah.
Welding can also give off fume, so we'd always recommend the use of fume extraction, such as the local one that we have there.
Right, power that up.
Okay. Now, for dip transfer, we'll use some quite thin material, in this case 3mm thick.
Yeah.
You can see that we have an oxide surface on the material. MIG welding is able to cope with that, but for very best results, you'd always clean that by grinding back to bare material.
Fine, okay.
The angles to be held for, in this case, this bead on plate, which is similar to a butt weld, are that in this plane, the torch must be directly overhead. But you have about a 15 or 20 degree lead on the torch from this vertical position so that you can observe the weld and see what's happening.
Right.
Stick out on dip transfer at this sort of amperage will be around 10mm. If you mind your eyes, okay,
Sounded a little odd to me there.
Yes, it is. That's got too much voltage or not enough wire for this particular dip welding condition that we're trying to set. You can see that there was a very long arc length, and rather than short-circuiting, the molten material was forming a ball on the end of the wire.
Yeah.
So if you would try turning the wire feed speed up to 8 meters a minute from the 4 meters that it was.
Okay.
You can see the ball on the end of the wire there.
Yes.
It's always advisable to snip the end of the wire before you start to make sure that you have a good start. Now let's try again, mind your eyes.
It's altogether more energetic. Lots of spatter, fairly straight bead as well.
Now that's certainly dip welding, the short circuit's taking place, but now there is too much wire for the amount of voltage that we have. And you can see on the weld bead itself, it's quite peaky, and as you commented, there was quite a bit of spatter there as well.
Yeah, so there's basically too much around there.
There's too much wire going into the weld pool.
Okay.
So if you would please turn that back to about 6 meters a minute, and let's see what we have there.
Okay.
Okay, mind your eyes.
Once again, spatter. Not so much smoke, but nonetheless, that
There, the
was more
sound
controlled.
of that weld was much better. It
Yeah.
really was short-circuiting quite nicely. And yes, please use that because it is hot. The weld bead itself is now reasonably well spread out, and there wasn't that much spatter being produced.
Right.
That, I would suggest, is a good balanced dip welding condition.
Good. What about the speed, Mel? You're keeping a fairly constant speed, are you?
Yeah, we can see the effects of travel speed. The travel speed is determined by the type of job that you're doing. Obviously,
Yeah.
on thinner material, you're likely to go quite a bit faster than you would on thicker material.
Yeah.
But we'll see the effect of speed. I'll do one run that's quite slow.
Already you can see a rather large pool appearing. Nonetheless, it's well in control there.
Hold it there. Not too bad, not too much spatter, quite a smooth surface, but you can see quite a heavy build-up, quite a wide spread.
Yeah.
If we go faster, mind your eyes.
Yes.
Okay.
Distinct difference
Now
there.
you can see a lot smaller bead, a lot less spread, so totally dependent on the application that you want. You might want a large bead like that, or you may need to go quite rapidly to produce a smaller weld bead.
Right, let's get rid of that in the bucket here. What now, can you take us through inductance again? The differences?
Differences on inductance. I suggested that the inductance tapping that we have was probably the right one for this type of work.
Yeah.
But now we have this good balanced condition. If you would just change the lead over to the lower inductance tapping and see the results that we get.
Okay.
Okay, mind your eyes.
Already there's a lot more noise. Seems to be spattering a lot more as well. And
Okay, so you can see it was a lot harsher sound to the
Certainly
short
was,
circuit,
yeah.
a lot more spatter produced, and if you would look at the edges of the weld there, how that looks quite cold compared to the previous weld bead on the other inductance tapping.
Yeah.
It isn't to say that inductance tapping doesn't have uses, it does in other applications, but in this application on carbon manganese steel, the higher inductance tapping is the better one to use.
Right, okay. So, if we put that back again, Now, we're talking about dip, globular and spray next. Do we need the same inductance? Do I need to put that back?
If you'd put the inductance tapping back up, because we're still going to be using a short circuit in this globular dip condition. What happens in globular transfer is that the wire occasionally short circuits the way that it does in dip welding, but it also has more voltage now, so it forms a globule on the end of the wire that drops across into the weld pool as well.
Yeah.
It does create quite a lot of spatter, and it isn't a condition that's used very often, but it is a condition in between dip and spray.
Right.
So
Just in case, I brought the other nozzle.
Okay, you've got a spray nozzle there. We'll put that on because we are going to go up to spray transfer after globular dip. Thank you. And if you would please put the wire feed speed up to around 10 meters a minute.
Right.
And we'll increase the voltage, but not too much. The figures on the outside of the machine here are indicating the open circuit voltage, and generally welding voltage is 6-8 volts below that.
Right.
Let's see if we have what's called a globular dip transfer here. If you mind your eyes.
Again, a distinct difference in what you hear and what you see. Rather a lot of spatter.
Okay, so you could still hear that short circuiting, the crackling taking place, but it was also the globules were forming on the end of the wire and coming across in free transfer. This is creating this spatter. It does have its uses, but it's very limited in globular transfer. Far more use is spray transfer, which we can do by increasing the wire feed speed again, in this case to maybe 12 meters a minute, and increasing the voltage even more. Let's see what sort of condition we have there. Just cut the end of the wire again. So mind your eyes.
Well, altogether less spatter and less noise this time round. It sounds more in control.
As you say, less spatter, less noise.
Yeah.
And that's not too bad a spray welding condition. We can trim a little more to get better effects.
Yeah.
You'll also have noticed that I used a longer stick out because it's higher amperage work, probably 18 millimeters, 18 to 20 millimeters. The effect, because we haven't ground this plate, you can see silicates on the surface. This is an additive to the wire that helps mop up any impurities there may be. For very best effect, of course, if we were to do that on ground plate, and I will just trim that voltage back a little to reduce the arc length. Snip the end of the wire, and let's see what we have now. Mind your eyes.
But as Mel said, it really is much more in control. Hardly any spatter. There's still smoke, of course, but that's been taken away by the
Okay, hold it
Unit
there.
next to me.
And there we have it. Nice, well spread, very low spatter.
Yeah.
And with spray transfer, quite high productivity as well.
Smashing. Okay. Shall we go on to welding some joints next?
Yeah, let's try a fillet weld. As I said before, there's mill scale and some oxide on this surface. It's probably advisable just to give that a light wire brush, just to get rid of anything that's loose on the surface. But still repeating that if you wanted very best results, we would grind back to clean material.
Yeah.
Okay, now we'll need to tack that up. In fact, would you like to have a go at this one?
Yeah. Okay.
Okay.
Let's try
Just
that out.
hold it in place. I'll hold it for you
Okay.
if you can tack up.
Right, I'll take the gun.
Okay, so mind your eyes. It's just a spot at either end to make the tack weld. That's good.
Okay.
And another one there.
Mind your eyes.
Okay. The condition itself can vary on the amount of stick out that you allow. As you have greater stick out, so on that particular wire feed setting, the current will drop.
Yeah.
If you go closer to it, the current will increase. So it's dependent on the stick out that you hold. I may need to just slightly adjust the machine to get an optimum condition.
But it is obviously a good idea to keep a steady hand as you go.
That's right. If you can put that torsion at around 45 degrees between on the 90-degree angle, get the wire right into the root of the weld and attempt to hold about an 18mm stick out.
Yeah. Okay. Try that then. Mind your eyes.
Okay, that's not bad. You can afford to slow down a little and let the weld spread across both plates. That's pretty good.
Okay, we hold it there.
Okay,
I could actually see material on the metal burning away on the edges there.
Yeah, that's this mill scale that we have there. I've been saying, it's better to have ground plate. In fact, let's try that on ground plate. But that's not a bad weld, perfectly serviceable.
Yeah.
And the reason why I'm trying to show it on the mill scale as well is that in reality, in practice, if you've got large jobs to do, it's unlikely that you grind all of the weld joints up.
Sure.
But the better results are going to be attained on ground plate. I'll just pop that into the bucket of water. This is for safety reasons to quench this hot material off.
Right.
It's not advisable to quench welds as soon as they're done. Now, I'll hold that again for you. And if you just tack either end for me, please.
Just take the trim off that. Okay, mind your eyes.
Okay.
Just take that off there.
And another tack at this end. That's good. Now, why don't you have a go at this one and see how we get on.
Right, same angle as before then.
Okay.
Just about there. Mind your eyes.
Nice steady travel speed. Keep that torch angle at 45.
Yep.
Okay, hold it there, Steve. You can immediately see the better surface appearance that we have now that we're not trying to fight this oxide and the mill scale all the time.
Yeah.
The only criticism that I had were that you were allowing the torch angle to drop a little so that you were unevenly distributing the wire on the plate.
I got some kind of, I went out of control at the beginning, I think. I wasn't quite in the right place to start off.
Yeah, because it's quite high amperage work, the wire is coming out quite fast,
Yeah.
and you really do have to set yourself for the start because as soon as the wire hits the plate, it wants
It's
to
off.
force your hand away.
Yes.
If you like, I'll just have a little go at that one if I may. Okay, mind your eyes.
Well, it's fine, nice and steady speed there. A lot of smoke that's
Been taken away by the extractor. Just
Now,
hold that with gloves and the pliers.
that's it, got the pliers on, so
Just,
that material is hot.
That's it.
Okay, if you could just turn it this way a little so I can see. There we've got reasonable travel speed, reasonably well-defined weld.
Yeah.
Maybe, again, I'm being critical of myself, I put too much on the bottom plate compared to the top. It really wants to be even spread on both sides of the plate.
Okay, Mel. Well, look, that's thick material. What about thin material? Can we carry on with this setup?
We could certainly use this machine, but it's quite likely that if we wanted to weld material such as here, we've got some 22 gauge or 0.9mm material.
Yeah.
1mm wire would be far too big for that. You could change that machine over and use 0.8 or even 0.6mm wire, but it's far more likely that you would use one of these smaller, lighter industrial units such as this one.
All right. So put that to one side.
It's very much the same setup as we had before, but in this case, a lot smaller power output. This is also single-phase supply compared to three-phase supply over there.
Yeah.
The wires inside the machine now, it's the same principle, comes into the line and the torch and is fed through. The controls on the front, there is the wire feed speed, or amperage in this case, and here's the voltage control. Instead of having the sliding voltage control that we had on the previous machine, this is stepped voltage control. And you'll probably find that each one of those steps is 1.5 to 2 arc volts.
Right. And the gas is set ready.
The gas we set on, but in this case, because we're going to be doing quite low amperage work, we set around 15 litres per minute. There's no need to have quite as much gas flow as on the higher amperage work.
Okay then. Well, if you set up the
We need to connect the earth lead to the bench to complete the electrical circuit.
power it up.
Turn the machine on, thank you. Now this is quite thin material, so I suggest we might have accidents and burning through it. It'd be a good idea just to set up on a couple of pieces of plate to allow a gap between this material and the bench. I've no idea what welding condition we have on here at the moment, so we'll just give it a go and see what we have. Mind your eyes.
Seems rather pulsy, not too much
You
spatter.
can see that problem that we had before on the first one, which is there's too much voltage there. The wire is not going into dip transfer, it's trying to form a globule to get into globular, and there's too much power there for that particular job. Let's turn the voltage back. Snip the end of the wire again. Mind your eyes.
Sounds a little more like welding.
There's certainly dip transfer taking place there.
Yeah.
But in effect now we've got too much wire for the amount of voltage that we've got on. There's not enough volts in that case. The dip was very harsh, and if we continued there'd probably be quite a bit of spatter. Let's give that some more voltage then. Perhaps to there. Try one more little run, mind your eyes.
Again, a subtly different sound, but still looking in
Not
control.
too bad, but
Yeah.
I suggest maybe just a little bit more wire feed speed on that. We should be able to get a good short circuit condition. Just get rid of this hot plate now, because on thin plate it's quite likely that once it overheats you can burn through very readily. And try again, mind your eyes.
That sounds spot on from here.
And there, that's a nice balanced
Yeah.
dip welding condition.
So,
You can see quite a flat weld bead, very little spatter. And on this material, this sort of thickness material, you really do have to move quite rapidly to prevent burn through.
as you say, that is a problem with thinner material. Is this the best way to weld thin material, do you think?
It's certainly the most commonly used way, but there are advantages in using synergic pulse machines for thin material. Synergic pulse machines also have big advantages in positional welding. There are some beliefs that the dip transfer in positional welding can lead to lack of fusion problems. To overcome this, if you use synergic pulse where you're simulating spray transfer but at far lower amperage than spray transfer can take place, there are benefits as far as fusion goes.
Okay, perhaps we can see that if we rig for that next then, Mel.
Okay.
Okay then, Mel, so we're rigged for some positional work now. What have we got on the bench here?
Yeah, we're going to do a butt weld in 25mm thick material, and to get penetration completely through the plate, we've had to put an edge preparation on. This has been flame cut. It's a 35-degree bevel, giving a 70-degree included angle. I've ground the plate for best results, of course, and also I've put a root face on there of about 1.5mm. This enables us to get control over the penetration bead. When we set the butt weld up, we're also going to be leaving a gap of between 3 and 4mm to allow that penetration bead to come through.
Okay, right, and so to the machinery.
The machine we're using is a synergic machine, and it has the ability to be used in dip and spray, and also in pulse.
Yeah.
Now, for the root run, I'm going to be using the dip transfer mode. This gives me good control over the penetration bead. Now, because of the fears of lack of fusion, particularly when you're filling out the joint with the complicated weave patterns that you have to use, then we'll be changing to synergic pulse. And for the root run, we're selecting dip. I've selected the program itself here. We're using 1mm wire, and I'm using a 1mm mild steel program that's in the machine already. The synergic knob is there, that's taking the amperage and voltage up and down, all on the one control. We've got a voltage trim here, and you can see I've selected quite a high voltage trim. This will not give that same sharp dip condition that we heard before. It's going to be quite a lot looser condition, but the more voltage means that I really do have no lack of fusion worries on this minor weave that we're putting into the root run itself.
Okay, fine, so it's just power on really, isn't it now?
Put the power on, yeah.
There we are.
And I set the conditions earlier and put a small run in here, and I think you can see on the root run here, at the end where I've stopped, I've had to grind the crater out. This is called feathering the crater. This enables me that when I start, I should get reasonably good pickup on the back of the penetration bead so that I have an even penetration bead. When I do start the weld, I'll be starting back on the previous run so that by the time I get into that ground section, the condition is operating very, very well. This will leave a small lump on the surface, but that's no worry, we'll grind that off afterwards.
Okay, fine, right.
It's very short stick out that we're going to be using, and I think you'll see me using just a slight side-to-side weaving motion just to ensure that I've got good fusion in at that weld.
Okay.
Mind your eyes. not a harsh dip, that's with plenty of voltage on it.
Right, Mel.
Okay, so you can see there's the lump that I was talking about. That's no problem, we'll grind it off afterwards, but
Yeah.
it's possible there's some lack of fusion in that. But by the time we got it into the crater itself, the weld was running well, and we've achieved good penetration on the back and a reasonable pickup.
Good.
You'll notice that there is some silicate on the surface of the weld. This is the addition that's added to the wire to help them up out of any impurities that there may be. Just scrape those off with a sharp blade, and it's always advisable just to have a quick wire brush in between the runs. As I say, before we weld completely over that, I'd grind that lump off.
Right, smashing. Okay, well, the next part of it is the weaving.
That's it. To fill up itself, the dip condition that we use there is going to be perfectly good for the root run. If we were to get these quite complicated weave patterns that we're going to need to fill this joint out, there is a risk of lack of fusion. So we'll use synergic pulse, where we're going to be using, in effect, an imitation spray transfer mode at very low amperages. Now, on the machine, we can select that on the button here. We're already at the moment in dip, so we go over into pulse. The program's already selected for 1mm mild steel wire, and from that previous little weld that I did, I know that these conditions are more or less set the same for pulse as they were for the dip.
Right.
So we'll come over and just snip the end of the wire, and we'll be building up on this weld here. Again, I'll probably start back on the previous run, which will leave a little lump that we'll grind off afterwards. But I'm going to be using a crescent weave, as it's known, where you raise the weave in the centre of the weld and dwell at the sides to ensure no undercut. This hopefully is going to produce a flat weld bead. I'll start back on the previous run again, so there'll be a small lump that we'll grind off. Right, if you mind your eyes. And you can hear the weld condition is completely different from that dip that we had before.
Hardly any splatter from here. Not too much smoke. A very well controlled weave. Going slowly up the work. Mel was describing, pausing on either side of the bead to make sure enough material reaches its destination.
Right.
Okay.
Excellent.
Hope you can see, reasonably flat, not too much need for dressing afterwards. We'll go through the inter-run cleaning again, scrape that silicate off, wire brush the surface, grind the lump off, and fill up.
Okay, Mel, that's the crescent weave. Are there any others?
Yes, there are. The crescent weave is fine for butt welds, but in the case of a fillet weld, if we were to try and use that weave, it's unlikely that we'll get good penetration right at the root. So in this case, we're going to use a triangular weave formation.
Right.
Just snip the end of the wire again. Okay, mind your eyes. So as you can see there, the wire is going right into the root, making sure we've got good penetration, dwelling at the sides to allow the weld to spread out and sit flat, keeping this triangle going to get good fusion all the way through.
I noticed that each time you're going up the work rather than down.
Yes. On any sort of thickness above, say, 3mm thick, you should always go vertically up to ensure good fusion and penetration. On 3mm and below, yes, you can more vertically down.
Right. Okay, so that's the weld procedure, is it?
This is for demonstration only. If we were doing a proper weld procedure, we'd certainly be restraining this by having strong backs on the back. This increases the mechanical strength of the weld. Other ways to increase the mechanical strength are to use flux core wires, for example.
Okay, for the moment, Mel, thank you very much. Before we see this process, let's explain flux cored arc welding.
Flux cored arc welding is a variant of gas metal arc welding, where the solid metal consumable filler wire is replaced with a tubular wire containing a core of metal powder or flux. The equipment used is the same as for gas metal arc welding, including the use of a shielding gas, although in some cases a self-shielded wire can be used. As its name implies, the wire is self-shielding, with the arc being protected by gases generated by the decomposition of the flux. Flux-cored wires are available for plain carbon and alloy steels, hard-facing alloys, and also stainless steel. But what are the benefits of their use, and what are they used for? Well, they offer the following advantages: slightly higher deposition rates compared to solid wire gas metal arc welding, and much more than manual metal arc welding. Alloying additions from the flux core, which affect the weld metal properties and operating characteristics, slag shielding and support, which can aid positional welding, and improved arc stabilization and shielding from the decomposition of the flux constituents. However, flux-cored wires have the disadvantage of a much higher cost than solid wires and greater fume formation rate, with more potentially toxic constituents, which must be controlled to comply with health and safety requirements. There are many applications for flux-cored wires, which include the joining of thick-section high-strength steels required for critical applications and high-speed mechanized welding. Hard-facing alloys are widely used for chemical plant, earth-moving, mining, quarrying, and agricultural equipment.
Now we're going to look at the practical aspects of flux-cored arc welding. Mel, you've made some changes. What exactly have you done?
Yeah, the previous welds that we've been doing have all been on a 3-component argon carbon dioxide oxygen mixture with varying levels of carbon dioxide as to the thickness of weld that we were doing. We're using rutile flux-cored wire here. Some are developed to run on CO2, but you generally get better results by using a 2-component argon carbon dioxide mixture.
Yeah.
This is the gas that we've set up. We've set a flow rate of around 20 litres per minute for this higher amperage work that we're doing.
Obviously you've changed the wire too.
The wire is, as I say, 1.2mm rutile flux-cored wire. We've had to change the wire feed rolls to accommodate that diameter.
Yeah, okay. Let's take a look at the joint we're going to work on. First
Okay.
of all, a lot of preparation here, first of all, isn't there?
Yeah, this is 50mm thick material, and we've got a double V preparation on this. We're going to fill up one side of weld, and we're not going to worry about what sort of penetration we're getting, because we'll turn the thing over, gouge out the back, till we get to hit sound metal again, and then fill up that side. That way we can ensure that we're going to get full fusion throughout the joint.
Yeah. Now this particular process generates a lot of fume, doesn't it?
Yes, it does. So we are going to use the fume extractor very closely over the work.
Right, well if I take the torch and we can
Yeah, do you want to do this?
set the machine? Yeah, okay.
Okay.
Switch the machine on.
Okay,
What about angles
well,
here, Mel?
the same way as you did before, Steve, moving from right to left, holding those torch angles the same. But this time, increase the stick out, maybe have about 25mm stick out.
Okay.
You want to spread the weld on both sides of the plate. You probably won't have to weave in this first pass that you're doing, but later on up the joint, you may well weave to bring both sides of the joint together.
Right, let's give it a try then. Put it nearly in place. Do I start on the part
Start
of the
on
old
the
weld
tack,
there?
yeah, and then run into the material.
Right, here we go then. Mind your eyes.
Just weave it slightly, slow down a little so it spreads on both plates. That's good. That's a little bit too much stick out. Go closer now. Go closer. Go closer. That's good there. Nice and steady, let it build up.
Okay, let's see what we have there.
I felt very comfortable actually once I got the levels right. Thank you for the guidance there. But
It's quite a nice spray condition that
Yeah,
you get off of these wires, and it is quite a pleasant weld. Now you see that we've got a slag cover on the
Yes.
weld there. We're going to have to remove that. It's certainly advisable to wear safety glasses while we chip that off.
right.
Okay, let's have a look and see what we have.
It comes up fairly readily.
It comes off reasonably easily. You probably do better with a standard chipping hammer rather than this blade, but it's coming off reasonably well.
Yeah.
Let's have a look and see what we have there. Oh, you've done a nice job. Join both edges. As I say, we're not too worried about how deep into the weld we went, because when we've completed this side, we'll turn it over, gouge out the material until we do hit this weld, and then fill up the other side.
Right.
It's a good job.
Thank you, Mel. Well, that's flux cord. Are there any other kinds of wires?
Yes, for thin materials, particularly in the car industry, there's been developed that process known as MIG brazing. These are using either silicon bronze or aluminium bronze wires. On the small industrial unit, I set up an aluminium bronze wire, it's 0.8mm diameter, and we'll try some of that thinner gauge 0.9mm thick material.
Okay, well, Rick, for that, have you changed the gas for this as well?
Yeah, the previous gas mixtures that we've used have had active ingredients such as carbon dioxide or oxygen. In this case, we're going to be using an inert mixture of helium and argon.
Okay, let's go for that then. Get some work on the bench ready.
Turn the machine on. Let's try with a lap joint. This is quite a typical joint that you'll find in the car industry. Just tack it at either end first. I'm treating it very much as you would a dip welding condition with solid carbon manganese steel wire.
Yeah.
Just tack there, tack here. Okay, so if you mind your eyes.
Really is very rapid progress.
That's the thing that you notice is how quick it is.
Yeah.
This has its advantage, of course, in that travel speed. And the way this material wants to flow means that you've got very little distortion compared to conventional welding. Its uses, as I say, in the car industry, furniture manufacture, bicycles, has its uses.
Marvellous. Mel, thank you. Well, that brings us to the end of this programme. You now have an understanding of carbon manganese steel and its applications, also how to prepare for welding and to weld using solid, flux cord and brazing wires. Shall we carry on, Mel, and do another joint?
You have just seen one of an expanding series of BOC training videos, which cover a wide range of cutting, welding and safety-related topics. To find out more, call free on 0800 515 661. That's 0800 515 661.